Hello students. So today in this lecture I will tell you the use of organopalladium reagents in organic synthesis. So mainly this organopalladium reagents, these are used in carbon-carbon coupling reactions, or we can write the cross carbon-carbon coupling reactions. So use in this cross carbon-carbon coupling reactions. Okay. So before 2010, this carbon-carbon coupling reactions, that was a tedious job. But in 2010, Suzuki, Richard Heck and Nagashi were the three scientists who were jointly given the Nobel Prize for discovering this carbon-carbon or cross carbon-carbon coupling reactions. So in this lecture we will discuss various types of these carbon-carbon coupling reactions. Now here in these reactions, this palladium 0, it acts as active catalyst. Active catalyst for these reactions. Okay, so during the reaction, this palladium 0, it converts up into the palladium 2 oxidation state, +2 oxidation state. So this palladium 0, this is unstable oxidation state of palladium, whereas this +2 is the stable, one of the stable oxidation state of the palladium. Okay, so if we write the various coupling reactions, we can write the various coupling reactions in a generalized form. So if I write it, then let's write it in generalized form. Suppose if we have this Rx as a substrate molecule, and in this R group, it may be any alkyl group, it may be alkyl, or it may be alkene, vinyl, aryl. So these are maybe these certain groups, and here this X may be X may be any leaving group. It may be iodine, it may be bromine, it may be chlorine, or some very good leaving group like O tosylate or O triplet. So these are the some leaving groups. So X is the here leaving group. Now this Rx in presence of this any other substrate molecule, it may be suppose I write it R dash this M. Okay, so here this R dash, it may be any alkyl, or it may be alkyne, it may be alkene, it may be alkene also, or it may be alkene, or I write it may be alkene, or it may be alkyne, like this. Okay, so these two, this in presence of palladium 0 as a catalyst. So palladium 0, suppose I write PD, suppose L2. So this L is any neutral ligand. Suppose L may be neutral ligand. Suppose one of the, suppose PPH3, triphenyl phosphine. This triphenyl phosphine is one of the ligands that we can use, or some other ligand. Okay. Now, and in presence of some base may be triethylamine or it may be triethylamine, it may be sodium ethoxide, it may be Na2CO3, sodium carbonate, and etc. Some base, these base can be used, and some solvent may be, suppose THF can be used as a solvent, benzene can be used as a solvent, dioxane can be used as a solvent, etc. These solvents can be used. So these two substrates, they combine to form this carbon-carbon coupling reaction between this R and this R that will take place. So carbon-carbon coupling reaction. So this R and one of this coupling will take place between this R and this R dash. Okay. So this is the coupling. This is the carbon-carbon coupling that happens. Okay. Now, so here this M in this M may be any metal. M may be, suppose I write this M, it may be, this is a metal, and depending upon this metal, suppose if metal is, suppose I write this metal boron. If boron is the metal, then the reaction is called as the Suzuki coupling reaction. And reaction is called as the Suzuki coupling. And if suppose I write it, the metal that I write, suppose it is a copper, then the reaction is Sono-Gashida coupling. Similarly, suppose if reaction occurs in presence of tin, then it is called as the Stille coupling. And suppose the reaction is your magnesium, then it is called as the Kumada coupling. And if suppose it is zinc, then this is called as the Negishi coupling. Negishi. So I think it's Negishi. This is Negishi coupling. Okay, and if it is silicon, then that is called as the Hiyama coupling. And suppose if only palladium is used, then such coupling is called as the Haack coupling. So if only palladium is used, then that is called as the Haack coupling reaction. So there are three scientists, that is this Suzuki and this Negishi and this Richard Haack. They were the three scientists who were given the Nobel Prize in 2010 for discovering these reactions. Otherwise, this carbon-carbon coupling reaction, it takes a lot of time and a lot of chemicals to convert to couple this carbon-carbon. Okay, so let's see the mechanism for this reaction. Okay. Okay, so if I write the mechanism, okay, so this mechanism, it involves three steps. Three steps which are involved. One of this mechanism, this is if we see in reactant and product, so there is no change in stereochemistry will occur during the mechanism or during the reaction. So one of the thing, no change in stereochemistry. No change in stereochemistry. In reactant and product. And okay. No change to one of this point. So three steps which are involved three steps which are involved in this mechanism. One is the oxidative addition. One is oxidative addition. One is the oxidative addition. In oxidative addition reaction, what I told you, the general reaction. The general reaction was, this was the general reaction when this Rx and plus this R dash M. So this was giving you the R dash as the product. So during the oxidation reaction, one of the things, this palladium it inserts between the Rx bond. So palladium metal insert between this Rx bond. So palladium insert between Rx bond, and the palladium which was present in a zero oxidation state here, that changes to plus 1 oxidation state. So palladium 0 changes to palladium plus 2 oxidation state. So this is one of the steps. And in second step, so in first step what I told you, this palladium insert between this Rx bond, and in second step transmetallation occurs. In second step transmetallation occurs. Transmetallation means the exchange of metal will occur. So exchange of metal from here, as you can see, suppose one of the metal is here copper. So copper will exchange from this palladium. So exchange of metal. Exchange of metal will occur. Exchange of metal, we can say exchange of metal, palladium metal, exchange of palladium metal with other metal. Exchange of palladium metal with other metal. With other metal. This is the second step. And in third step, reductive elimination occurs. Reductive elimination. So in reductive elimination, one of the thing in final this step, the carbon-carbon coupling takes place. One of the thing, CC coupling occur. CC coupling occur. And second thing, that elimination of one of the HX molecule will occur. Elimination of here one of the HX molecule will eliminate here. So elimination of HX molecule and this palladium 0. Palladium which was first it was present in zero oxidation state, then it converts during the oxidative addition, it converts into plus 2 oxidation state, and finally this metal, this catalyst will removed as again in a zero oxidation state. So elimination of HX and palladium 0 will occur. Okay. And third thing that we can write, this coupling occur and elimination occur. Elimination of this occur means, or we can say the palladium which was present in plus 2 oxidation state, palladium which was converted into plus 2 oxidation state again get converted to plus 0 oxidation state. So elimination of HX and palladium 0. So reductive elimination. Reductive means a palladium which was present in plus 2 get reduction into the 0 oxidation state. So these are the three steps that you will see in the mechanism. So let's see the mechanism here. Okay, so let's see. Suppose if we have this Rx. Okay, then this in presence of suppose this palladium triphenylphosphine. So I write this thing as a catalyst. When here this palladium is present in zero oxidation state, now this palladium get insert between this R and X. So PD and this, this R palladium get inserted here, and we have this 2-triphenylphosphine ligand over here. Okay, now, so this is the second step. This is the second step. Now in third step, what I told you, so this is the transmetallation will occur. So transmetallation will occur. So suppose this is R dash M, and transmetallation, the exchange of metal will take place. So exchange of metal. Here, as you can see, palladium was zero oxidation state. Now this is present in +2 oxidation state here. Okay, so +2 oxidation state. This has a minus charge in comparison to this PD. This carbon will also have a minus charge. So, and these are the two neutral ligands. So that's why the palladium here it is present in +2 oxidation state. And now this exchange of metal will occur. So exchange of metal that will takes place. So R, this is PD, and we can write here R dash. Okay, plus this is here. So this is a transmetallation step, and in third step, reductive elimination. So this is oxidative addition. This is transmetallation. And this reductive elimination will occur. Reductive elimination will occur here, and these in reductive elimination, these bonds will break, and these two are this carbon-carbon coupling in this will occur. So this is R dash, and plus this PD, this catalyst degenerates here. Okay, so this is a simple mechanism for this carbon-carbon coupling reaction. Okay, so if you will see here this example, so if we see, let's see the example here. So this is one of the examples. As you can see here, Sn is present. So what I told you, if one of the palladium 0 is present and Sn is present here. So if palladium 0 and Sn is present, then the reaction is called as in presence of tin. The reaction is called as the Stille coupling. So this reaction, this is the example of Stille coupling. This is the example of Stille coupling. And so what will happen? So this is benzyl bromide. So even here this R, what I told you, R may be an alkyl, alkene, alkyne, vinyl, okay, maybe aryl, maybe benzyl. So suppose this is a benzyl is present over here, and the reaction, this carbon and here this carbon will undergo coupling. This carbon and this carbon, this bromine will leave out. And the coupling between this carbon and this carbon will occur. So what we can do, simply just join this in product. Just join this carbon and this carbon, and the product, you will get this product. After removing this bromine, we will get this product. Okay. So the products, so writing the product is very simple here. So in the same way, if we write this one, so some base may be present over here, Now if we write this one, so in this case, this bromine will leave out, this hydrogen will also leave out, this base may abstract out this hydrogen, and finally HBr is moved, so base will abstract this hydrogen also, even it will neutralize this acid which is formed during the reaction. So this is the utilization of this base here. This is the utilization of base here. So base will abstract this hydrogen, and HBr which is formed during the reaction, so that would be neutralized by this triethylamine as a base. So what should be the product? The writing the product is very simple. Again, as I told, this during this process the stereochemistry will remain unchanged. Okay, stereochemistry will remain unchanged in the product. So just we will remove this hydrogen and connect this carbon, and connect this benzene carbon and with this carbon, and that would be the product. Simply we can write the product. Okay, so in the same way, in this reaction, the product that we can write, because here no other metal, so here metal given is silicon is given, so that's why the name of this reaction, this would be the Hiyama coupling, this would be the Hiyama coupling. And here, as no other metal is present, so this is an example of Hack coupling reaction. So this is an example of Hack coupling reaction. We will also see the mechanism of this Hack coupling reaction. Now here, if you will see, one of the metal which is present, is boron is a metal over here. Boron is present as a metal. So since boron is present, that's why this is a Suzuki coupling. So this is the example of Suzuki coupling reaction. So no doubt this bromine will leave out. So bromine will leave out, and the coupling will take place between this carbon and this one. This carbon and this one. So this carbon and this one, coupling will occur between this. So if we write the product, and product would be something like this. So this would be the product. In this case, we can write the product in simply we can write the product here. So this would be the product in this case. Here, if you want to write the product, so the product would be NH2 over here, NH2, and this is carbon. So yeah, this would be the product. Okay. Now, so now let's see this one example. In this example, still again this SN. So this is also an example of Stille coupling. Both reflect with the group. This will leave out, and this carbon will attach to this one. This carbon will attach to, the coupling will take place between this carbon and this carbon. Now, so in this case, as you can see, let's correct it. If you will see, then here this carbonyl group is present, carbon monoxide of carbonyl group. This reaction takes place in presence of CO. So let's see this reaction, because in this reaction, this is CO. Carbonyl will get inserted between this R and R. Carbonyl will get inserted between this R and R. Okay, so you will see the mechanism of this one also. Now, if you will see this reaction, then this is also the palladium is only the this metal, other metal. So that's why this is a Hack coupling reaction. This is the example of Hack coupling reaction. Now, if we see, let's see when carbon monoxide is given here. When carbonyl, how this carbonyl get inserted in the reaction. Okay, so let's see. If I write the general reaction, then suppose if we have this Rx and R-M and this PD, suppose some base is present over here, some solvent is present over here, and in this case, and this carbonyl is also there. So this is carbonyl, it will get inserted. Migratory insertion of this will occur. Migratory insertion of this carbonyl group will take place. So this would be the product in this case. So let's see the mechanism of this one. So mechanism is very much similar. One extra step would be there, migratory insertion of this carbonyl group. So 3 steps that will remain same. That is, one of the step is oxidative addition, and then second step would be the migratory insertion of this carbonyl group. Third step would be transmetallation, and then fourth step will be the reductive elimination. So these are the four steps in this case. These are the 4 steps in this case. So if I write the mechanism, then so first of all we have this Rx, and this in presence of suppose palladium 0 catalyst. So this palladium will get inserted, or oxidative addition will occur. Oxidative addition. So R, P, D, X, L, L. These are the 2 neutral ligands. Now second step will be the insertion of carbon monoxide. So insertion of carbonyl group. Suppose this would be the minus, minus charge. So in this step, this will tap over with the d orbital of this, and so what we can write, PD, this is R, PD, L, X, minus charge will come over the palladium, and we have carbonyl plus charge. Okay, now in next step, the transmetallation will occur in next step. So if we have this R dash M, then this R dash will now combine with this PD. So we have R, PD, L, minus MX, and minus charge over here. Okay. So now in next step, so now after this step, the transmetallation will occur. So if we have this R dash M, then PD, L, and this will be R dash, and here we have this transmetallation. Okay. Now minus, right? Now this migratory insertion of this carbonyl will occur. So we can write migratory insertion of this carbonyl. So plus, if we have this carbonyl, so we can write migratory insertion of carbonyl. So this will attack over this empty d orbital of palladium. Palladium will have the minus charge. So what we can write, R, PD, minus charge will come over the PD, L, this is L, R dash, and C, this will be triple bond O. Okay, so now what will happen? So this positive charge will get neutralized, and now this will get migrated to this carbon. This R will get migrated to the carbon, and finally what we can write? We can write PD, R dash, L, and this will be carbon. Now this is the another R. This carbon will get converted into double bond, Okay, this will get converted into the double bond. So now, so in next step, reductive elimination. Next step, reductive elimination happen. So reductive elimination. In reductive elimination. So here the product that we get after this reductive elimination, that would be, so here reductive elimination, one of this palladium catalyst will get removed. So how it is removed? One of the bond will break from here, another bond will break from here, and this carbon and this R, the joining, the coupling between this carbon and this R dash will occur. So finally this PDL2, the catalyst has regenerated, and the coupling occurs between this carbon of this carbonyl and this R dash. So what we can write the product, so COR dash, so this would finally be the product. So if carbonyl group is present in the reaction, then it will get migrated within the this R and R dash. So same is the this problem. If you see this problem, then in this problem the this carbon CO, this carbonyl group is given in the reaction, and this will get inserted between this carbon and this carbon. So if you see the product that we will see, this is the product. Here you can see this carbonyl group is inserted. Okay, so this is about the reaction when carbonyl group is present in the reaction. Now let's come to the Hague coupling, mechanism of this Hague coupling. Now in Hague coupling, what I told you, in Hague coupling other metal is not present, only the palladium metal is present in a Hague coupling reaction. So, and one of the important thing in like I told you, in all other coupling reaction, the stereochemistry of reactant and product that remains same, but here in Hague coupling usually either we get a trans product, usually we get trans product. Okay, trans product, usually we get the trans product. Now suppose if I write the general reaction, suppose this is Rx, where R may be any alkyl, alkyl, okay, it may be aryl or it may be benzyl, okay, alkyne may be there, and plus if we have this group. So in this case, this Y, this X is the leaving group, and Y it may be any electron withdrawing group or electron releasing group. R may be electron withdrawing group or R may be electron releasing group, and we have palladium 0 as a catalyst. So the product for this reaction, coupling will occur, carbon-carbon coupling will occur. So this carbon may couple either with this carbon or with this carbon. So either here or either here. So this depends upon the nature of this group, whether it is electron withdrawing group or it is electron releasing group. So the product that we can write, suppose it is the electron withdrawing group, suppose this Y is the electron withdrawing group, then in that case the product that I can write, that would be I can write this type of product. Okay, or let's see the mechanism for this one. Let's see the mechanism. So if I write the mechanism, then first of all this Rx, and first step is the oxidative addition. And this palladium will get this will get oxidized to plus 0 to plus 2 oxidation state, and it will get add within this Rx bond. So this is PD, this is X. So palladium get inserted between Rx bond, and this is two ligands. Okay. Now in next step what we can write, we have suppose this group and the substrate. Now if you see, then this palladium will have here this delta positive charge, and this corresponding to this will have the delta negative charge. Now if here Y is electron withdrawing group, suppose I say this Y is electron withdrawing group, if Y is electron withdrawing group, then this will have the delta negative charge is carbon, and this carbon will have the delta positive charge. So how it will add? So the addition will occur in a syn manner, that is syn addition will occur. Addition will be the syn addition, means this R and this palladium will add on the same side of this double bond. Okay, and this double bond will get converted into the single bond. So if you see, this is Y, then this corresponding to this delta negative charge, the addition of this palladium metal will take place, L, and this is X. Whereas on delta positive charge, this R will get attached. And suppose here we have H and H. Now in next step, this beta hydride elimination will occur. In next step, beta hydride elimination. In beta hydride elimination, the beta bond means hydrogen which is present on the beta carbon. So suppose this is the alpha carbon, and this will be the beta carbon, and this hydrogen will be the beta carbon. So hydrogen, before this beta hydride elimination, so what will happen? So this hydrogen and this one, that should be on the same side. So this bond rotation around this carbon-carbon single bond is possible. So what we can write now? This is Y, PB, LLX, and here after rotation, this one of the hydrogen will go on this side, and now we can write this thing. Okay, now in next step, this hydrogen will get removed, and this palladium will get regenerated as a PDL2 catalyst minus HX. This HX, that would be neutralized by the base, so that's why we may have some base over here. Some base may be there, that would be removed, neutralized. Okay, and finally this PDL2, this is also removed, and the product that we can write is this will be this product. This will be the, okay. So this is the Haack coupling mechanism, and the same, if you see in this example, so this is an example of Haack coupling reaction where only palladium is present. And same with this is also the example of Haack coupling reaction, only palladium metal is present. So what you have to do, only join, remove this hydrogen and join this one and this one, and according to this mechanism, see whether you will get the trans product or not. In the same way, remove this one here and join this carbon and this carbon, and we will get the products. Just join this one and this one, and we will get the trans product. Okay, thank you.